So these first few were, I think, pretty straightforward, stuff we've done in class. In fact, they all are aromatic, with possible exception of the first one. Okay. So these are aromatic. That's right. Four n plus 2, right? 14 is 4n plus 2 when n equals 3. So that is a Huckel number. The issue with the first one is that it may not be flat. Right? It may not be flat. Couple reasons it may not be flat. Primarily, you're dealing with hydrogen-hydrogen interactions here. Okay. Now, it can be flat, because as we know, you can have, that would be like the sort of a diene that would undergo a Diels-Alder type reaction. It can be flat, but the question then becomes, does the aromaticity, does the conjugation outweigh the steric interactions, or will it slightly turn? And in a molecule this big, so when I wrote the question, I was thinking, yeah, it's aromatic. But in a molecule this big, it's probably likely to twist, to turn a bit. I think it talks about that in the book.
Yeah, the book specifically says it's not planar.
Yeah, because anything this big is really not going to be planar. Because the energy barriers to twisting is just too low. It's easy for it to twist and get, as opposed to a small ring where it can be higher energy for it to twist. So I'll accept either answer for this one. The only one that's definitely not correct is anti-aromatic.
Can you explain why they're aromatic? Like, I understand why.
Yes. Okay, so this one, you've got 6 pi electrons, right? And you've got p orbitals on every carbon. Okay. Here, this is pyridine. It has a lone pair, but that lone pair is not in the pi system. It's out in an sp3 orbital, which I think we talked about a little bit in class. It's also, there's a picture of it in your book. Thiophene has 2 lone pairs, one of which ends up in a p orbital. The other one ends up in an sp2 hybrid orbital. Right, 2 per lone pair. So one lone pair contributes to the pi system, the other doesn't. And then this one does contribute to the pi system. Okay. Names. This one should have been, whoops, not ortho. Meta, bromo, aniline. No, but I'll accept that. It's A and I. And this one is ortho nitrotoluene. Yeah, these are the best names. These are the names that you should use. However, right, you can also name these numbers 1, 3, or 1, 2.
What if you said like bromo, nitrobenzene?
For this one?
Yeah.
That's not nitrobenzene.
Sure.
Nitrobenzene is NO2. Okay, and then the synthesis. Some interesting things going on here. Primarily, the strange thing is that it looks as though an oxygen has kind of been inserted between these 2 carbons. And of course, we don't really know any reactions that do that. So what's really probably happening here is that we're doing some kind of a reaction to cleave that, to get rid of some carbon, and then end up with oxygen on there. This being at the benzylic position, that is the carbon next to benzene, you have some options because there are some special reactions from chapter 18 that deal with chemistry at that carbon. And that's kind of what I was getting to here. And I see some of you, many of you are using those types of reactions, which is great. So here's how I think of something like this. Of course, there are various ways to make ethers, but perhaps the most direct, or the one that we talked about the most, is making it from the alcohol through substitution chemistry, or through a halide, also through substitution chemistry, right? I'll try this one first. If we want to go look, if we want to look at the other one, that's fine too, where you deprotonate it and then react with some kind of substitution substrate. Okay, so now where do we get this benzylic alcohol coming from here? Well, there are various ways to do this. I see some of your ideas were great, like brominating at the benzylic position and then eliminating and doing ozonolysis to break off a carbon. That's certainly one cleavage reaction. But a special cleavage reaction that's even easier to do, because ozonolysis is a little tricky sometimes lab-wise, is to oxidize. One of the interesting reactions that we looked at was that you can actually oxidize any alkyl groups, well, most alkyl groups, as long as there are hydrogens there, into carboxylic acids. And there were a couple different conditions that we used for that, such as chromic acid was one, or potassium permanganate was the other. And you can either put in as chromic acid or as the actual reagents that you would use, the dichromate, the sulfuric acid, since we don't usually just buy chromic acid on its own. So this is then fairly trivial. We know we can reduce acids with lithium aluminum hydride. Okay. And if you really wanted to be efficient, you might be able to do this in one pot and realize that after this, you have an O minus there. After the reduction, it's an O minus, which means you really don't need to then protonate and deprotonate again. You could potentially just add the methyl iodide and do the substitution when it's already deprotonated. Whether or not that works well is an experimental concern, but from a paper standpoint, that seems like it would be a good idea. Okay? Questions about that? All right, let's move on. Okay, so last week we talked about these types of benzene issues. So we'll have another quiz on this stuff. Let's do it on. And do it on Monday or Wednesday?
No, Wednesday.
Wednesday. Okay, and then we have an exam the following Monday. The exam's Monday this time. Note that, not Wednesday. Not a week from today. 2 weeks from today.
This is this Wednesday or next Wednesday?
The quiz will be next Wednesday.
Which chapter is the test of?
Through chapter 19.
And what's the quiz next Wednesday?
Same.
Chapter 19.
Yeah, we'll probably be done with it by, actually, we may actually like get through the actual material today or Wednesday, but we're going to spend some time just practicing it and doing a lot of different problems because there are so many reactions here. So we'll be working on this pretty much up until the test. All right, so recall from last week. Hopefully you got a chance to study some of this stuff over the weekend. The functions of these directing groups. You can have the activating groups, the deactivating groups, depending on the electronic makeup and what they do to the ring. We mentioned first about activating groups and how an activating group like methyl, which is weakly activating, can stabilize the intermediate in a way that that a regular benzene can't. And we talked about how it stabilizes it at the ortho and para positions. All right. And then we looked at how something like a methoxy group is strongly activating because of the lone pairs that it puts in the ring. And we looked at how something like a nitro group is strongly deactivating in the way that it pulls electron density out of the ring. So here's a question then, kind of summing this up. If you were to take this molecule and brominate it, what would you get? So you got a couple questions to answer here. There are two rings, and they're not the same. So you have to decide which ring is likely to be brominated. And then you have to decide where on that ring it's in fact going to be brominated. So see if you can write down what you expect is the major product or products of this reaction. What is it that's different? Let's start with this. What is it that's different about the two rings? Well, there's no benzylic positions exactly. I mean, there is kind of on the one. But yeah, the substituents are effectively different, right? What type of a substituent is on the ring on the left? What type of a group would you, if you just isolated that and you're just looking at this part here, what sort of thing is that? Is that going to be a withdrawing group that's deactivating or a donating group that's activating? Deactivating, right? Because we can draw resonance just like with a nitro group that pulls electrons out of the ring up to that oxygen. And so what about the other ring? Activating. So what does that tell you about which ring is likely to be added to? The one on the right. The one on the right is activated toward electrophilic substitution. The one on the left is deactivated against electrophilic substitution. All right. So if the one on the right is activated, what positions are activated? Why?
Because if you draw the conjugate of that, there'll be a positive, more positive charge in the meta positions than the ortho para. So then the bromine, since that makes it electrophilic, so since the bromine's like a negative charge, will more likely attack them.
Okay, almost correct, except opposite. Not everything you said. Most of it was right. The only part that's wrong is that in this type of reaction, bromine is the electrophile and the benzene is the nucleophile. Because it's Br2, it's not Br minus. Remember, the benzene goes and attacks. So it's the opposite. And actually, you're right that the positive charges are on the meta positions, but what we actually are directed to is the negative positions, which is the ortho and para positions. Yeah. So the resonance reasoning was correct, just you get the flip, you flip the charge. Yeah, let's go back up and check it out. Well, okay, let's just draw it. I don't know where it was up there. So we can draw resonance here, something like that. And that negative charge going up to the ortho position, and that can also be passed to the para position, shows that that's actually most susceptible, since that's the thing that's going to be attacking the electrophile. So the likely products here are the ortho and para addition to the ring on the right. Okay. We're going to keep practicing this.
Which one's more prevalent?
Hard to say in this case. My guess would be that the para is more prevalent because of the steric interactions of this larger thing hanging around there. But that's something we really need experimental data to verify. Okay, let's try something else. So now what happens if you have multiple substituents on a ring and then you add to it? We're going to look at a couple different ones of these. All right, so what if we take this, what would be the name of this molecule? Right, para-nitrotoluene. So what happens if you brominate para-nitrotoluene? Where does the bromine go, and why? To what? To what? No, there are two different substituents. Yeah, ortho to the methyl group. Why? That's right. One substituent is activating, one substituent is deactivating, but they both are actually directing to the same place, right? A methyl group is an ortho-para director. Can't substitute para because that position's taken. A nitro group is a meta director. And the positions meta to the nitro group are here and here. And the positions ortho to the nitro or to the methyl group are also here and here. So both groups are actually acting together to direct the bromine to the same place. Okay. So now what happens if they're not acting together? Let's try, well, we'll leave that up there as a reference. What about this one? Where do you expect the bromine to go in this case? Any one of the four spots. Sure. What do you think is going to be the major product? Why? Okay, so there could be some steric issues here. And that's true, that you always have to look for steric issues. However, oftentimes what happens is one group will be a better director than the other, we can say. Meaning it has a stronger influence over the resonance of the ring. Remember that these things are basically resonance type effects, right? So if one of these can have a greater stabilization of the intermediate than the other, that's what we would expect to favor. Okay, so let's look at those two intermediates. Let's try the two possible products and then we'll figure it out. So here are the two possible products. And then let's look at the intermediates that lead to those products, as we did before.
I'm not sure, but does any dipole or anything else play a role to like electronegativity or dipole?
Yeah. Sorry, would you like me to be more specific? Yeah, we're going to talk about that in a second. Yeah. So let's look at kind of the most stable resonance form of each of these intermediates. And that is the one that's stabilized by the substituent. So that's these two. If you don't believe me in that, or you don't understand where that came from, make a note to draw out your own resonance forms when you're studying as well. All right. So what's happening here? Which of those two resonance forms, or not resonance forms, which of those two intermediates is more stable? How many people say the one on the left is more stable? How many people say the one on the right? All right, why the left?
So because the oxygen on the alcohol, right, pulls more of the negative charge towards it, making the carbonyl more positive, making the carbon attached to the oxygen positive.
Okay. But it's already positive, right? So by your logic, that would destabilize it. But you're not totally wrong.
I think bromine can, at metabolism can share, I mean it has as side electrons too that can share negativity which it cannot with oxygen because oxygen has.
Well, remember, we care more about stabilizing the carbocation. That's what's the key here, right?
Isn't the right one more stable because methyl group is electron donating, so it's going to stabilize the positive charge?
That's true. It stabilizes the positive charge, but in fact, the oxygen stabilizes the positive charge even more. So remember, I don't know if you remember, we said this a long time ago. I don't even remember what the context was. But we were talking about how resonance effects are almost always more important than inductive effects. Effects of electron moving via resonance are always going to be greater stabilizing than electronegative stuff pulling stuff away. So in fact, the one on the left is more stable, but not because of an inductive electron pull effect, because of a resonance effect. Let's look at how this is stabilized through resonance. All right. So that positive charge can be moved up to the oxygen, which we know can stabilize a positive charge reasonably well. And that's something that can't happen in this other one. This cation is you know, it's stabilized relative to benzene because that methyl group is somewhat electron donating through what we call hyperconjugation. But it's nowhere near as stabilized as something that has a true resonance form that can move that positive charge around, which is what we have in this oxygen here. So that's going to be more stable. And so the favored product is this one here. And in general, let's go back to our chart from before. if we look at this chart from the book of the strong, moderate, and weak activators, and then the weak, strong, moderate, and weak deactivators, a strong one is always going to direct more strongly than a weaker one. So something like this with an oxygen on it is always going to direct more strongly than something like this with just the methyl group there. All right. And that's kind of the key to that previous problem. Okay. So let's try another one, and then we'll talk about halogens a bit. Well, okay, let's summarize that so we have some words here. What's going on? Can't change colors? All right. So stronger directing groups, we'll say they win. All right? When there's a conflict between the two, the stronger directing groups win. All right. What if there's not that sort of conflict? What if it's two similar type directing groups? What's going on here? So what about that one? What do you see there? Again, two possibilities, right? Is there much of a difference in the directing power of these two substituents? Two possibilities here, right? So would you expect to see one more than the other, or should they be split about evenly if those both have similar directing abilities? What do you think? All right, well, fine.
Well,
Use your that's okay. I don't have a problem with that. We'll just look at these right here. What do you see? Do you see a difference, or do you expect that they should be about the same, since I'm telling you the directing abilities are about the same?
And the CH is a meta director?
No, they're both orthopara directors.
Okay.
Yeah. Any R group is going to be an orthopara
Well,
director.
I think the one on the right would be more prevalent. because,
Why?
The carbocation will eventually make its way to that 2' position.
Up here, you mean? Actually, in this case, it won't. It can't do that from resonance. To do that would require a hydride shift. That would break the aromaticity and be unlikely to occur. So actually, both of these groups stabilize the carbocation about the same. So does that mean we would expect equal numbers of products? Or would you still expect to see one more than the other?
Does the state influence play any role in this?
What do you think?
So the one in the paraposition
Yeah.
is more bulky than
That's right.
that.
So that's what ends up controlling this. The major product is this one because of steric effects. You see some steric hindrance here from that larger isopropyl group. And the larger the group that you're putting on there, the larger the electrophile, the more of an effect this will have. But yeah, when the groups have similar directing abilities, then you look for things like sterics. Okay. Let's try another one. Now there are 3 distinct positions that the nitro group could add to. Which is going to be the major product? It will be so you're saying this one? That's the major product? Why that one?
Because you have both, you have all three groups are considered, what's the word, activating.
Mm-hmm.
So then, if they're all the same, then you're going to want to look at the biggest group like you said.
Well, I wouldn't say they're all the same. They're all activating, but we know the oxygen-containing groups are much stronger directing than the carbon one. Does that change anything?
No, well, no, it's still be over there.
Okay.
And then the steric hindrance would push it to that side of it because you can have, it would be further away from the second.
Okay. Anybody else want to add to that?
I mean, I think it's it can be here because of the less steric because of this side.
Okay. All right, so remember, you're all right, and this is the right answer. But be careful a little bit, because electronic effects can be stronger than steric effects. Steric effects are easy to see and easy to grab onto, because you may not be as comfortable looking at activating versus deactivating groups and stuff. But that can be more important sometimes. So let's look at this group by group. We know that the OHs are much stronger activators than the alkyl group here. Okay, so we would expect that the most likely positions are the ones where an OH group can direct either ortho or para to it. So this OH group directs here and here. Of course, that one's taken up. And this one, which is also taken up. This OH group here directs to this ortho position and this para position. So you actually have an OH group directing to all 3 of those possible positions, which makes them roughly equivalent. Now we could also say that this group isn't completely unimportant, right? It directs ortho para as well, so it actually reinforces these 2 positions electronically, and then can't direct there because something's there. However, then the steric issue comes in here. It may be unlikely to substitute ortho to such a large group. So this is probably the major product. So here's a question then. What do you think is the second most likely product? Or what should be the most major minor product? Which one next? This bottom position or the one over on the right? Why on the right?
No, not right, because the directing still gets
Well, in both cases, actually, you have the same directing, right? This one is directed to by both this OH and this group and the sec-butyl. This position is directed to by also this OH and the sec-butyl. Does that change your answer at all? Yeah, so the second most one should probably be this one, again, for the steric reasons. In fact, let's make a note of this here. We rarely see substitution in between two groups like that because of the steric hindrance issues. So you almost always see that would be the least likely position, even when it's electronically favored. Okay. So now what happens if you actually want to put groups in those kinds of places? What if you want to make a product that is particularly not favored? Let's take a look at this one. Let's say you have this tert-butyl group on benzene. And we want to brominate ortho to that group. Now, simply reacting that with bromine and a catalyst is not going to do that for all the reasons we talked about. It's going to highly favor the para position because of sterics. But remember, when we're doing these syntheses, we can find ways around all of these problems. And one clever way to get around this problem is to sort of use a protecting group type chemistry. We're going to block this position, and then do this, and then unblock it. And one way that's pretty nice and convenient to do that is with the sulfonic acid. So if we make a sulfonic acid with fuming sulfuric acid, that'll be directed to the para position. Because of all the stuff we've just been talking about. That group is an ortho, the tert-butyl group is an ortho-para director, and it's pretty bulky. So we'll direct down there. Then, whoops, we can do our addition. There's only one position that this can go to. One that's directed to by both groups. Even though it's a little bit sterically blocked, there's simply no other choice because it's directed to by both groups. So the only real possible product here is this one. And then, if you recall, you can eliminate off or resubstitute off the sulfonic acid with dilute sulfuric acid. Whoops. There we go. And that's a nice way to actually get that product that you want. So when you see things blocked like that, that might be a good, or when you see something that seems impossible, like, oh, I don't know of anything that we can do to actually do that because of the steric issues, that's when you can break out this blocking group and use it to your advantage. All right. So, questions about that stuff? Okay.
Are there any other, like, blocking groups that we use?
Not that are as easy to get off. So I think the book pretty much just focuses on this one. I think we'll stick with that too. All right, so one last thing, and then we'll kind of summarize it all up. And that is the halogen directing and activating. Halogens are a little bit weird where they fit in here. We mentioned this last time on that table that they're kind of the middle ground. Well, let's talk about why that is. So I'm actually moving back in the book if you're following along here. I skipped over this initially. The book doesn't talk about this a whole lot, but let's look at something like this. Chlorobenzene. Would you expect that chlorine to be activating or deactivating? Why deactivate?
Because what's the, you use it to like, it takes some of the negative charge away, so it pulls the negative charge away, so it allows more negative charge to spread throughout the molecule.
Right. It's inductively withdrawing. Yeah. Yeah. Halogens, being somewhat electronegative, pull electron density toward them, and they tend to stabilize negative charges and destabilize positive charges. So when you have something like this, you would expect it to be deactivating because any intermediate that puts a positive charge here is going to be inductively destabilized. Relative to benzene. Right. We want things that are electron donating to stabilize these, not electron withdrawing. So, okay, fine. So halogens are deactivators. Now, the electronegativity of halogens, other than fluorine, is sometimes, I think we probably do this in first semester chemistry, organic, it's a little bit over-exaggerated. They're actually not that electronegative. I mean, if you think of solvents like chloroform, dichloromethane, the organic solvents that we use, they're not that polar. They're not, right? They dissolve, use normal kind of organic stuff. So the carbon-chlorine bond or carbon-bromine bond is really not that polar. But it's just enough to make it worse than a carbon-hydrogen bond. Right? So it is a little more polar than a carbon-hydrogen bond. So these halogens are weakly deactivating. Yes, they're deactivating relative to benzene, but not so much that it makes it difficult to do the reaction like strongly deactivating groups like nitro groups are. Okay, but here's where it gets weird. The other deactivating groups we've seen are all metadirectors, but halogens are actually orthoparadirectors. So we'll say, but they are orthopara directing. And that's because they still have lone pairs. And even though the resonance isn't a real strong contributor, it does in fact lead to a slight difference in charge around the ring. So to that end, if you further halogenate something like a chlorobenzene, you tend to get the ortho and para products. So that's kind of the strange middle ground there. Okay, so if we go back to our chart now, we've talked about all this stuff. Oops. All the stuff in this chart, from the strong activators, the moderate activators, and the weak activators, which are orthoparadirectors, to the halogens, which are actually deactivating reactivity-wise, but still orthoparadirectors. So you'll notice the line separating orthopara from metadirectors is under the halogens. The line separating the activators from deactivators is above the halogens. And then we talked about these more strongly deactivating things as well. All right.